All right, the next section is on phase diagrams. Phase diagrams are sort of graphical representations of how various substances behave under different conditions. So in other words, what conditions of temperature and pressure will the substance be a solid? And what conditions will cause it to be a liquid? And which will cause it to be a gas? And where are the transitions between these phases? These can be very useful when dealing with substances or when wanting to know, what substance or what phase you want a substance in. What I've reproduced here in a fairly crude way is the phase diagram for water. It's also shown in the textbook in a much nicer version than I could draw, so you could look at that if you like to, if you'd like to. And you'll notice that there are regions that are labeled solid, liquid, and gas. And that's because these are the regions where the substance, in this case water, is stable as those particular phases. So notice that conditions of low temperature, that is, temperature is the x-axis and pressure is the y-axis. So you notice that conditions of low temperature, which would be over at the left, and high pressure, which would be up, tend to favor solid. Whereas conditions of high temperature over here on the right and low pressure down toward the bottom would tend to favor the gas phase. And that's exactly what we'd expect. And that's generally the way that the phase diagrams for most substances are arranged. The exact positions of the lines will change a little bit. The exact locations of the triple point and the critical point, which I'll explain in a moment, can change a little bit from one substance to another. And actually, one very unusual thing about water is the fact that this line between solid and liquid leans to the left. I've kind of exaggerated the lean. It doesn't lean that much to the left. But for most substances, it actually leans a little bit to the right. The reason that it leans to the left is that for water, water is the only common substance where the liquid is actually more dense than the solid. And so some conditions of high pressure will actually favor liquid in water rather than solid. Normally for most substances, the line goes more like that way rather than this way. And this is, like I said, it's just an artifact of the fact that liquid is more dense than solids. You'll notice that the lines between phases I've also labeled with what they're generally called by people who use phase diagrams a lot. The line between solid and liquid is known as the fusion curve, which makes sense because the transition from solid to liquid is fusion. The line between the solid phase and the gas phase is known as the sublimation curve, because going from solid to gas is sublimation. The phase between liquid and gas is known as the vapor pressure curve or the vaporization curve, because again, going from liquid to gas is vaporization. Okay, if the substance is in a certain phase and you change the conditions of pressure and temperature, you can always tell what's going to happen to the substance by finding the new location on the phase diagram. And so if you change the pressure and temperature of water from, say, a value that's over here, which would be ice or solid water, to values that are found, say, over here, then the water is going to sublime from solid directly to gas. If you change the conditions from someplace that's, say, here in the liquid region to a combination of pressure and temperature that would be, say, here in the solid region, well, then the liquid is going to freeze and become a solid. And so you basically just trace a path from the original conditions to the final conditions, and you can see what's going to happen. Okay, so the lines basically crossing a line would be a phase change. So if you go from, say, here to here, you've crossed the fusion curve, so you've undergone fusion or melting. And going from a solid to a liquid is melting. So that makes sense. The triple point, it gives the temperature and pressure at which all three phases of the substance are in equilibrium. And most phase diagrams have a triple point somewhere on them. But they're at different locations depending on what the substance is. For water, at the triple point, the pressure is 4.58 torr. That's 4.58 torr, mind you, not atmospheres. So this is actually a very low pressure. And the temperature is 0.0098 degrees Celsius. So it's a fairly low temperature too. You don't actually have to remember that, but that's just sort of showing you that at that combination of pressure and temperature, solid, liquid, and gaseous water would all be in equilibrium with each other. Okay, and the critical point would give you the temperature and pressure above which the substance is a supercritical fluid. And a supercritical fluid, I don't think we really need to go in great detail into what a supercritical fluid is, but it's sort of a unique phase of matter that has some properties of liquid and some properties of gases and some properties that are kind of in between liquids and gases. And they're really a sort of a very big area of interest for researchers now, because supercritical fluids can do a lot of things that that other substances can't. They can also do a lot of things that other substances can do, but the supercritical fluids are often more environmentally friendly than the substances that were previously used. Like one use for supercritical carbon dioxide, for example, is extracting caffeine from coffee for making decaf. And they used to use things like chloroform for that, which is pretty nasty stuff. It's hard to dispose of safely, and it's a suspected carcinogen. So you'd probably rather not have it used in your coffee. Something that you're going to be drinking. Supercritical carbon dioxide has also been used to some extent for dry cleaning clothes, that can't be washed with water. Well, what they used to do is they used to use stuff like dichloromethane or methylene chloride, as it's often called. And that is a similar compound to chloroform, actually, and that is also a suspected carcinogen. So it's good to be able to avoid using things like that. Navigating around in a phase diagram. Well, I already mentioned some of this stuff. Is basically you can determine what will happen when the conditions change just by finding the original position in terms of temperature and pressure and drawing a straight line to the new conditions. And again, if you cross a line, that's a phase change. So for example, if the temperature of the water at 1 atmosphere increases from minus 50 degrees Celsius to 150 degrees Celsius, what'll happen? Well, that's actually line A here. If you start at minus 150 at 760 torr, that's 1 atmosphere. You're in the solid region. As you proceed, when you get to 0 degrees Celsius, the substance melts, and the temperature momentarily stops rising while the water is melting, and it becomes a liquid. And continuing on, when you get to 100 degrees Celsius, the water starts to boil, and the temperature again stops rising until the water is completely boiled off. But then, assuming that you've captured the steam and you're able to keep heating it, you keep right on going until you get to 150 Celsius, which is somewhere out here, at which point the water is a gas. Okay. So the water would start out as a solid. It melts to a liquid at 0 degrees Celsius because we're talking 1 atmosphere here. And then boils to a vapor at 100 degrees Celsius. And it reaches 150 degrees Celsius as a vapor. Or in other words, gas. Another example might be if the pressure at 25 degrees Celsius is lowered from 1 atmosphere to, say, 0, and that's the B line above, the substance starts out as a liquid because we're starting out right there, and that's in the liquid region. And it becomes a gas. The temperature at which that would happen would be 25 degrees Celsius, and the pressure would be the pressure that's directly across here. I'll just call it P1. Because I don't know what that pressure would be, and this diagram is not drawn to scale, so it's really not easy to figure out what that pressure would be by figuring out how far below the 760 it is on the graph. So we'll just call that P1. And from that point on down, it's a gas. And that'll be a gas the rest of the way down until it gets to the bottom axis, which would be 0 pressure. I'm saying approximately equal to 0 because there's really no such thing as totally, completely 0 pressure. Okay? All right. There are phase diagrams, of course, for other substances. The book shows iodine and carbon dioxide. The main difference between them is, for one thing, the fusion curve for both of those substances leans to the right instead of to the left, because, of course, those substances act like most substances in that the solid is more dense than the liquid, not the other way around. And you'll notice that carbon dioxide has no stable liquid phase at 1 atmosphere, regardless of the temperature. The lowest pressure at which you can have liquid carbon dioxide at any temperature is about 5 atmospheres. And that's why dry ice sublimes at normal, atmospheric pressure. Okay, I think that suffices that for that. Section 11.9 is about water. Water gets its own section in the book because it's an extremely important substance, and it's also kind of a weird substance in a lot of ways, one of which we just mentioned. The liquid is more dense than the solid. There's no other common substance for which that's true. I'm not aware of any substance for which that's true, but I'm sure there must be 1 or 2 others. But certainly nothing that's anywhere near as common as water has those properties. So that is one thing that makes it weird right there. Water also is uncommonly common, so to speak. It has properties that make it extremely useful. It dissolves an extraordinarily large number of things. And so, it makes sense to take a moment and have a look at water. So water is not only very common, but it's very important. Water covers something like 2/3, maybe even a little more of the water's surface. It makes up something like 70% of our body mass. It's totally essential for life as we know it. No liquid water, no life. It's also known in chemistry as the universal solvent because it dissolves so many things. In general chemistry, most of what we actually do is chemistry of aqueous solutions, that is stuff dissolved in water. And so some of its unusual properties include the fact that it has a really low molar mass, low enough that it really should be a gas at room temperature and atmospheric pressure. But it's not because of hydrogen bonding. So not only are the hydrogen bonds strong, but they're numerous in water. Water is also a small molecule, and that's one of the reasons why it can engage in a lot of hydrogen bonding. And it has hydrogen directly bonded to oxygen, which is sort of a prime example of hydrogen bonding. The water molecules are polar, which allows water to dissolve many polar substances, and also ionic substances. To some extent, it can even dissolve some nonpolar substances. And those would be things like oxygen and carbon dioxide. That's really important because, and the way it does it is through induced dipoles. The dipole in water, because water is a polar molecule, so water has a permanent dipole. When certain other nonpolar molecules like oxygen and carbon dioxide come close to a water molecule, the water molecule's dipole can induce a dipole in the nonpolar molecules by sort of causing the electron distribution in the nonpolar molecule to become temporarily skewed in a way that causes the nonpolar molecule to be attracted to the water, even though water is polar. And so that's called an induced dipole. And that can allow stuff like oxygen, carbon dioxide to dissolve in water to a pretty fair extent. And that's really important because that's very important for water, or for life to be able to exist in water. Aquatic animals like fish have to, basically their gills filter the oxygen out of the water. And if water were not able to dissolve a significant amount of oxygen, then the fish wouldn't be able to breathe. Aquatic plants require carbon dioxide out of the water. And so if water were not able to dissolve a significant amount of carbon dioxide, then aquatic plants would die. And so it's pretty lucky that it can. Okay. Okay. And water has a relatively high specific heat capacity. That is liquid water. If you remember from when we totaled up the energy to heat up a mole of water from -25 to 125, the specific heat capacity for liquid water is 4.184 joules per gram degrees Celsius. And that means it takes a lot of energy to warm water up. And when water cools down, it gives off a lot of energy. And this is significant in a lot of ways. Water is very effective as a coolant. And that's only liquid water, though, by the way. Solid water and gaseous water have actually fairly low specific heat capacities. So that means that water is an effective coolant both for our bodies and for artificial machinery like cars, car engines, because water is able to absorb a lot of heat from its surroundings without changing very much in temperature. And when water does evaporate, like from your skin, it takes a lot of heat with it. And so it's very, evaporating sweat is very effective in cooling us down. And also, large bodies of water are very effective in moderating climate. They act as basically heat sinks, meaning that a lot of excess heat during the summer can be drained off by the water, and the water can then return some of that heat to the nearby surrounding land during the winter. If you look at, the book gives some examples, like for instance, if you look at year-round temperatures in someplace like San Francisco versus someplace that's about the same position as far as north-south goes, but inland a distance, like Sacramento. Summers in San Francisco are much cooler than they are in Sacramento, even though Sacramento is no further south than San Francisco is. It's just that San Francisco is on the ocean. And the water, the water in the ocean absorbs a lot of heat from the atmosphere that would otherwise go into the land. The same is actually true here in Buffalo. As kind of hot and humid as our summers seem to be, try going inland a certain distance. I grew up in Elmira, and I know from experience that the summers there, even though it's really not that far from Buffalo, it's far enough away from the lakes that summers there are really quite a bit hotter than they are here in Buffalo. And also, winters there are quite a bit colder than they are here in Buffalo, at least in terms of temperature. Here in Buffalo, it's the wind chill that kills you. But if you take the wind away, the temperatures in Buffalo are actually quite moderate during the winter time. And again, that's because of the presence of the lakes. All that water is slowly returning some of the heat that it absorbed during the summer back to the land during the winter. Okay, so and another factor with water is, of course, the fact that the solid form is less dense than the liquid. And that is very unusual. This is because the crystal structure of ice requires the molecules to move a little bit further apart than they normally are in liquid water. And this has some pretty significant consequences also. First of all, ice floats because it's less dense than liquid water. That may not seem like a great thing if you're a passenger on the Titanic, but it is actually a good thing overall, because if ice didn't float, if it sank to the bottom of rivers and lakes, it would kill all of the life in those rivers and lakes every winter. Or at least, the fish would have to migrate a lot more than they actually do. With ice floating on top, it actually provides kind of a layer of insulation, and it helps prevent freezing deeper down. And so the plants and the fish can stay around, and there's sort of less impact on the environment every winter than there would be if ice were more dense than water and sank to the bottom. So that would be kind of a major disruption in the life cycle every winter if ice sank. There are downsides to that. because the fact that water expands when it freezes, that makes freezing of biological tissues very dangerous. So like, for instance, frostbite is really dangerous because it basically freezes the water in the cells in your body. And when that water in the cells freezes, it expands and it bursts the cells. It just breaks right through the cell membranes. And once that happens, the cells are dead and they're not coming back. And that's a really bad thing. And so that's why frostbite is so dangerous. Also, even fruits and vegetables that get frozen can be damaged because the water expands as it freezes. So damage to frozen foods. So it does have its downside, but overall it's probably a good thing. Okay, so that's a quick look at the water. We're at 30 minutes now, so have to break for the next segment. I'll be right back.